All right, good evening, everyone. It's Mr. Haynes again. Well, looks like we have one more day off, but we have to continue on. Just a reminder, if you did not look at the notes and the practice sheet from yesterday, you are officially behind. Coach Brisson and I will not be covering those notes in class. The video and what we did yesterday is covering that information, just like this video and practice sheet is going to be covering this information. The next time we're in, we are going on with future material. Please make sure you are keeping up with that. Also, please don't forget, you remember that assignment that was going to take 3 weeks, those AP progress checks? Guess what? They're due this coming Sunday. So if you haven't worked on those yet, you still got time, but you need to get that done if you've not done so already. All right, so for today, what we're going to do is we're now going to take these unit circle values that we've learned about, and we are going to translate them into a graph. So what does it look like when we, for example, as we are rotating around the unit circle? So imagine the unit circle going around either in the positive direction or in the negative direction. Imagine the patterns of only the y coordinates, the up or down that happens. So for example, at 0, we know that it's not up or down. So the sign of 0 is 0. And then we go to pi over 6, and pi over 6 has a sign value of 1/2. So the next y coordinate would be 1/2. All the way up to when we're at pi over 2, that's going to have a y value of 1. Then when we go to 2 pi over 3 and 5 pi over 6, the y values start decreasing again. They go back down to root 3 over 2 and root 2 over 2. All the way back down to pi, they're at 0. Then the y values turn negative. What we're going to be doing today is we're going to be graphing these things. We're going to do it by hand the first time so that you get a basic idea. And then I'm also going to show you on the graphing calculator what it has, what it's available to do. So you'll have to excuse me. I'm going to be flipping between multiple screens trying to make sure that this works. All right, so to start us off here, what I would like for you to do is pause the video, and on your thing you will notice that you have a table of values here, and you'll notice that all of those tables of all of those values I've given you are all unit circle values, and you can see that I have given you a table that starts at 0 radians, and then at the end of the second line it finishes at 2 pi radians. Now notice at the top it says round output to 2 decimal places for easier plotting. So on this graph that's down here at the bottom, you're going to be plotting these points as you get them. Now, are you going to be able to plot them exactly where they need to be? No. I mean, you'll be able to plot 1/2 and you'll be able to plot 1, but the other ones like square root 2 over 2 and square root 3 over 2, you're going to have to roughly estimate where those are. So if you would, take a moment and pause the video, go through. You can use your calculator to help you get these values, change them into decimals, fill them into the table, and I'll come back in just a moment and we'll talk about the graph. All right, okay, hopefully you have plotted these values and you have gotten some numbers. One thing I do want to note is maybe how you could use your graphing calculator to help you get these values. Notice I've made a note here on the side. The theta scale, the angles that are the inputs, notice is pi over 12 radians. Notice that all of these unit circle values from 0, which you could say is 0 over 1, for example, pi over 6, pi over 4, pi over 3, etc. Notice all of those denominators are multiples of 12. So is there a way we could use our graphing calculator to help us get these values quickly? All right, so I'm going to see if the graphing calculator can help me with this. So I'm just going to go into the y equals, and I'm going to put in sine of x. And remember, we need the table, so I'll press second graph for table. All right, you'll notice that's not very helpful. 0 radians, okay, but 1 radian, 2 radians, 3 radians, that doesn't really help you. So let's change the scale in our table, and to do that, we're going to go second window into the table set. Still going to start at 0, that's fine, but for this delta TBL, that's the Greek letter delta, means change in table, I'm going to change that to pi over 12. And notice that it automatically changes that to a decimal for me. Now I'm going to go back to my table, so second graph. So here's 0 radians again. Now this first one would be pi over 12. Well, okay, that's nice, but that doesn't really help us. The next one would be 2 pi over 12. What is that in lowest terms? That's pi over 6. So pi over 6 has a y value of 0.5. The next one is 3 pi over 12, which would be pi over 4. That's also on your table, 0.7071. By the way, if you need to see more decimal points for these aren't all just to 4 decimal places. If I arrow over and highlight the y coordinate, you'll notice that it gives the entire y value that you're going to need here for any of these. 0.5 is exact. You know that from the unit circle. And then there's 0.7071, that's square root 3 over 2. I think that's square root 3 over 2, I believe. And it's something like that. Anyway, you kind of get the, actually, wait a minute, I'm sorry. Let me just do 2 pi over 2, pi over 6. I'm sorry, this is square root 2 over 2 here. I'm sorry, that's square root 3 over 2. Okay, the 0.8660. So anyway, these are the relative tables that you're going to put into your table, or that you're going to put onto your graph. So if you plot those points, all right, flipping back. So now when you get through with your graph, you should have something that looks like this. You notice the wave pattern that we have here, where this starts at 0 and 0 radians has a value of 0, and then the y coordinates increase, then the y coordinates decrease, they continue to decrease down to 3 pi over 2, and then they increase back up to 2 pi. And notice that if we continued this on, if I went on past 2 pi, you notice the y coordinates would just repeat themselves again, because it would just be another lap around the unit circle. So actually what you have done is you have graphed one period of the sine of x or sine of theta graph. This is a periodic function. Hence the reason we covered periodic at the beginning of this section. So looking here is a basic representation of the sine graph. You graphed it from 0 to 2 pi, but notice that if you went to negative theta values, or even past 2 pi radians, the pattern is going to repeat itself over and over again. By the way, what is this pattern called? What is this wave pattern called? The special name for it is sinusoidal. So you can see it listed up here. So that's going to describe the shape of this graph. It's called sinusoidal. And you can see the definition there if you're interested in it. If we were to go through and to do our various properties, you notice that the domain is all real numbers. No matter what angle we put in, we can always get a sine value for it. The range, notice the y values. The lowest y value on the standard sine graph is -1, the highest is +1, and then it can take on all of the y values in between. So the range is, notice this is an interval notation, bracket, -1, 1, bracket. The period, remember the period from us learning about periodic functions, that's how long it takes for one cycle of the graph to happen. That is 2 pi is going to be the distance that is needed. By the way, going back to odd and even, I believe we talked about that briefly, that an odd function has what we call origin symmetry. So if you imagine any point, you could draw a straight line through the origin and have a mirror image point. So for example, this point has a mirror image of this point. This one here has a mirror image over here, and you could draw a straight line through those points, and they always pass through the origin. Okay. And also down here at the bottom, notice if we use some of our fancy AP pre-calculus language, as input values increase, the sine function oscillates. That's what we call that wave pattern happening over and over again. It's called oscillations. And notice it changes between concave down and concave up, and it will continue changing from concave down to concave up to concave down to concave up over and over and over again. And then remember, what are these points called where it changes from concave up to concave down, or concave down to concave up? Yep, those are points of inflection. So sine curves also have points of inflection that you might have to have some information about. By the way, I'm not sure if your notes have this or not. I can't remember. Listed up here, This is going to be the general function for a sine curve later on when we start talking about transformations. Remember transformations? We have vertical shifts, we have horizontal, let me use my fancy language. We have vertical translations, we have horizontal translations, we have horizontal dilations, and we have vertical dilations. For right now, you are not responsible for any of those. Currently, your responsibility is, can you reproduce this nice, pretty, basic sine graph? All right, going back to our calculator, we used our calculator earlier to get our table. Can we also use the calculator to produce a graph? Well, certainly we can. So I've got y equals sine of x. If I press graph just like it is, there is the wave pattern that we usually look at, and you produce the wave pattern from 0 to 2 pi. Notice this is a little bit hard to look at. It's a little bit narrow. If you ever are going to graph a trig function on your calculator, if you go up here to zoom, one of your options is option 7, which is called z-trig or zoom trig. So if you ever graph a trigonometric function, very often it is helpful to use zoom trig as a way to look at the graph a little bit better. So if I select zoom trig, notice it's a little bit easier to see the graph. You also notice it looks like the graph is actually passing through at particular points. But be careful, that's no longer 1, 2, 3, 4, 5. Let's take a look at the window and see what happened. All right, we kind of have some interesting numbers that are here. Now this negative 8.63 to positive 8.63, so those would be numbers of radians. I believe that is approximately, I forgot what the exact number is, but it's more than 2 pi. It might actually be something like 9 pi over 2 or something like that. I'm not sure why the calculator chooses this. But, however, what I do want to point out is here for the scale, notice we've got the 1.5707, etc. Like, what is that? If I'm not mistaken, that should be pi over 4. And I am mistaken. It wasn't pi over 4. It's double that, pi over 2. Sorry about that. So notice that when you do zoom trig, it automatically changes our x-axis to line up better with radian measure, mainly going by pi over 2. Each x mark on the graph is a pi over 2 length. Notice also it narrows down our y minimum and y maximum, and it just goes by 1. So notice if we go back to our graph, we have a nice, looking graph that we have. If we want to go back and make sure the graph looks like what we just graphed on our sheet, we could change the x minimum to 0. We could change the x maximum to 2 pi. There we go. And if we want to make sure to get all of the little marks like we saw before, maybe I change this to pi over 12. That'll make sure to capture all of the different unit circle values. So now if I do a graph, let's change our window. Let's make our y's a little bit easier to see. I'm going to go from -2 to +2. And in fact, if we want to make it look like our thing, I'm going to go by 0.25. All right, so this should reproduce your graph. Here is pi over 6 here. Here would be pi over 4. Then we have pi over 3. Skip 1, we're at pi over 2. We're back at 1, etc. So notice you can always go back and change the graph for what you need. So play around with it a little bit, and I hope that kind of works out for you. But remember, you can always do zoom 7 for zoom trig. That always gives a nice window for you to view in. And if you always want to change it back, of course, you can do zoom standard number 6 to get back to your traditional viewing window. All right, and then one final item here, as I have it listed here. Very often when we describe the graph of sine, we're going to talk about it this way. We're going to talk about what happens to our output values when we start at theta equals 0. Notice this graph, we start off in the middle of the graph. It goes to a high point at 1, comes back to the middle at 0, back to a low point, -1, and then back to the middle at 2 pi. Now, later on, when we do transformations on this graph, if you have to graph a basic sine curve, it's going to be a good thing to remember that generally sine curves, without a reflection of some sort, it's going to start in the middle, go to a high point, it's back to the middle halfway through its period, then it's at the low point, back to the middle to finish its period. All right, so we just graphed the sine function. What do you think's happening next? Yep, that's the cosine function. So take what we have learned before, go back and look if you need to, and fill in these values. Use your calculator if you need to help you out to get the decimal values, and we'll come back and look at the graph. Okay, hopefully you were able to plot those points. Hopefully you saw the wave pattern again, but notice this time when you look at the graph, it looks a little bit different. At 0 radians, notice that the x values, the cosine values, start off at 1. So actually, if you think about the unit circle, you're thinking about the side-to-side motion of the points as they revolve around the circle. So notice you start at an x value of 1. As you get straight up to the angle pi over 2 on the unit circle, it has an x coordinate of 0. When you're facing to the left at pi, it has an x coordinate of -1. And then back to x being 0 when the angle has a terminal side straight down, finally getting back to an x value of 1 when we cycle back to 2 pi. Once again, if you used your graphing calculator, here would be the values for the cosine function. And notice that the same y values happen, they're just in a slightly different order. All right, here is our general cosine curve. By the way, cosine, the shape of the cosine curve, is also called sinusoidal. So basically, as long as the graph can be made as a transformation of the sine curve, then we describe the graph as sinusoidal. So later on, you can probably tell that there's a horizontal translation involved, and we'll talk about the fancy names for that a little bit later. But since the cosine graph is just a horizontal translation of the sine graph, it is also called sinusoidal. Once again, you'll notice the domain is all real numbers. Every angle will have a cosine value. Range is the same. The lowest x coordinate you can have is -1. The highest x coordinate is 1, so that is your range. The period, once again, it takes 2 pi units for one cycle of the curve to happen. Once again, up here, this is what the general cosine curve is going to look like with all the different transformations. Like I said, for right now, you only need to know the basic cosine curve. That's it. We'll talk about transformations if we get a chance to meet on Friday. Notice what is slightly different here. Remember that when we did sine earlier, it started in the middle at 0. However, this one actually starts at its high point 1. Then the sine curve went up high. Well, this one goes back down to the middle, and then it's to the low point halfway through its cycle, back to the middle and back to high. So sine was middle, high, middle, low, middle, whereas cosine starts high, goes to the middle, low halfway through, back to the middle, finishes at the high point to complete one period. Also, cosine is referred to as an even function because it has y-axis symmetry. If you think of the y-axis as a mirror, you'll notice that the mirror reflection on this side will look just like the left-hand side over here. And just like the sine function did before, if we see the note down at the bottom, this graph is going to continually oscillate between concave down and concave up. Okay, those are our basic notes on the basic sine curve and the basic cosine curve. What I want to do before I let you go is I want to go through a couple of questions on the practice sheet just so you can kind of get an idea of how they work. All right, here's going to be the practice sheet that you're going to be working on. Some of these questions are a little different maybe than you're used to, and I just want to go through a couple of questions to kind of give you an idea of how they work. And by the way, you may be thinking, wow, this is wordy and all this. Hey, this is AP pre-calculus language, so this is what the College Board's going to be giving you. You just have to take your time and parse it out. And all of you are very capable of doing this, but you do have to do that, four-letter word, read. All right, let's take a look. So we're given an angle alpha in standard position, and notice they've been nice enough. They have given that to you in gray there, so you can very clearly see the angle that they gave to you. Notice they don't tell us exactly what it is. I mean, could it be 2 pi over 3? Maybe, but it might be shorter than that. But we don't know. The function g is given by g of a equals cosine of a. Okay, so in other words, we're going to be looking at cosine values. And remember, what are cosine values? Cosine values, when we're looking at a circle, you're looking at x values. So keep that in mind as we are working through this question. We're going to be comparing x values. So for example, for our angle theta, what would probably be the x value associated with it? Well, it's to the left of the y-axis, so it has to have a negative x coordinate. Is it negative 1/2? Is it negative 1? I don't know. But I think it's safe to say that it's negative. All right, continuing on. For the angle alpha, that's the lowercase Greek letter alpha that's not shown. Okay, what is this statement telling us? So let me change the color here so I can draw on it. So angle alpha here in the middle, it has to be bigger than our given angle theta. So it's going to have a larger measure than our blue angle that I have circled, but it cannot be any bigger than 3 pi over 2. All right, so our angle theta is going to be somewhere where it has a terminal side, maybe somewhere over here. We don't know where, but somewhere in this region. Sorry about that, because for some reason I tap on it and it starts zooming and then all of my stuff vanishes. Sorry about that. All right, so our angle, just like I was talking about here, so our angle alpha, I'll just redraw that here, somewhere over here. And I'll be careful not to have the zoom feature come on top of me all of a sudden again. All right, which of the following is true? All right, g of alpha, okay? So this is the x coordinate that goes along with our green angle, is less than the x coordinate that goes with our given angle, which is over here. Well, think about it. Let's take a look at this. Now, keep in mind, if this statement is true, it has to be true every single time. So if I can come up with a counterexample of any type, then this isn't true. All right, what do I mean by that? Okay, well, I'm going to use my green here. So is it possible for the x-coordinate of the alpha angle to be smaller than the x-coordinate for our given angle? Yeah, it could be. If the terminal side for our alpha angle was right down here, it wasn't quite at 3 pi over 2. Notice its x-coordinate would be its x-coordinate is further to the right on the number line than our given angle. So yeah, that's possible. However, what if our alpha angle instead had a terminal side over here? Well, what do you notice about its x-coordinate? Its x-coordinate would be a quote-unquote larger negative number, maybe -3, -4, while our theta angle is only the -1/2 or -1, which would make it smaller. So I can draw one alpha angle and it would have a bigger x-coordinate. I can draw a different alpha angle and it has a smaller x-coordinate. So what does that tell you about this first statement? Is it absolutely true? No, we don't know. So that's not true. Look at letter B. It says the x-coordinate for the alpha angle is bigger than the x-coordinate for the theta angle. Well, we just showed that earlier. If the angle was very, very steep here, then yeah, we could make that true. However, if it's over here to the side where I drew it before, it's not true. So this is not true. Could angle alpha and angle theta have the same x-coordinate? They could, but is that necessarily true? If I draw all the possible angle alphas, they won't necessarily be equal to each other. Look at option D. Depending on the value of alpha, sometimes its x-coordinate is smaller than theta's, and sometimes it's bigger than theta's. Yes, depending on where I draw the terminal side, depending on where I draw that green, and remember, that green I can draw anywhere in here I want to, just as long as it satisfies that. All of these x-coordinates can be bigger or smaller than the theta x-coordinate. So letter D is going to be your best answer choice for that. All right, so looking at our practice sheet that's here, and let me get the scale back where I want it. Well, we'll just go with it here. So question 1 we just went through. Question 2 and question 3 are similar. Now I go down here to questions 4 through 8 and questions 9 through 13. All of these are questions about the basic cosine curve and the basic sine curve, and they are asking you about concavity and increasing and decreasing. So in each of these blanks, for each of these intervals, you're going to say whether the graph is increasing, concave up, decreasing, concave down, increasing, concave down, decreasing, concave up, something like that. That's what you're writing in all these blanks. Now, one more question I wanted to go over here is down here at the bottom, what's listed as question 14 and question 15. I want to do question 14 together. It says, for the function cosine theta, so that's our basic cosine curve, what are, notice this, here's a particular word we need to watch out for, and it's particular. What are all values of the domain where f of theta equals 1? So here's what we know about the cosine curve. Now, we only drew the cosine curve from 0 to 2 pi. However, what's the domain of the cosine curve? Well, we can take as many laps around the unit circle as we want to in either direction. It's all real numbers. This says list all values where the function value is equal to 1. There's infinitely many of those. It keeps happening over and over and over again. How are you going to write them all down? Mr. Haynes, this is a digital day. We don't have all this time. Your video is already going too long. Well, I'm going to introduce a notation to kind of help us here. Well, first of all, let's get an answer for just our regular graph. So if you go back and look at your cosine curve, you'll notice that if theta is equal to 0, that is going to have a cosine value of 1. And then we also notice that at 2 pi, well, crud, this thing starts zooming. I'm sorry about that. I don't know why. So, okay, let me draw. Sorry, my stylus here is not very good. So 0 and 2 pi. But by the way, it's also going to be 4 pi. It's also going to be 6 pi. Every time we lap around the circle, we're going to get to that starting point that has an output value of 1. So how do we write this? So the way I'm going to write this answer is going to look like this. I'm going to say theta equals 0 plus 2 pi k. I'm going to put a comma, and then I'm going to note that k is, and don't you love my handwriting on this stylus screen? It's beautiful, isn't it? Oh yeah, that's not creepy looking handwriting, is it? Okay, what did I just write? So theta equals 0. Now notice 0 is our first angle that has the property we want, that its output value is 1. Its cosine value, because cosine of 0 is 1. You've been working with your unit circle values. So that's my starting point here. And then I said plus 2 pi k. Now you might say, oh, you're using 2 pi because one of our other answers here was 2 pi. Actually, that's not why I'm using 2 pi. What is special about 2 pi when it comes to the cosine curve? It's the period of the graph. And what do we know happens if we go a period length either to the left or to the right of a value? That means we're going to get back to another value that has exactly the same answer. So what have I written here? I've said, okay, the angles that are the answers are 0 plus any period. And what's this k where k is an integer? Well, think about it. Let's say k is 0. Then 2 times pi times 0 is 0. Theta equals 0. Yes, that's one of the angles. What if k is equal to 1? 0 plus 2 pi is 2 pi. Yes, that would be an angle that has that answer. What if k was 2? That'd be 0 plus 4 pi. Yes, 4 pi is an angle that has this property. And then I could go on up to 3. Yes, 6 pi has it. 8 pi has that. 10 pi has it. In addition, why does k have to be an integer? Well, what if k was negative 1? 0 plus negative 2 pi is negative 2 pi. If we went to negative 2 pi, we'd be right back to where we started. It would also have an output value of 1. So what 2 pi k does is it basically says every period multiple will also work. So we just need to establish a starting point, which is 0. By the way, in this answer, would you have to write 0? No. Could you just write 2 times pi times k? Sure. You say, well, how do we get angle 0? Well, 0 is an integer, so if we replaced k with 0, 2 times pi 0, 0, that would be one of the answers. So for this number 14, what are all values of the domain? We would write it as theta equals 0 plus 2 pi k, comma, k is an integer. Do I have to write k is an integer, Mr. Haynes? Yes, because somebody who's just reading your work, if you just write the k and you leave it alone, they don't know what k is. It's not written in the original problem anywhere. We can't see anything. So you're going to see as we work with this, we're going to have to give repeated values. And remember, what started us off? Why were we having to deal with all this? What did the question say? It said, what are all values of the domain where this happens? So you're going to get used to this 2 pi k notation as we go through. So number 15 is going to be similar, except you're going to be working with the sine function, so your answer should be a similar format. Okay, I think I have covered everything we need. Please try out this practice sheet. Remember, you can reach out to either Coach Brisson or to me to get answers to your question. Please make sure that you're keeping up with your work. Please don't fall behind because we are going to keep moving when we get back to school. Hope all of you have a good day off. Stay warm, stay safe, and I'll talk to you later.